Okay, so hello everyone. This is Wednesday, March 18th. Excuse me. And here, Mr. Guy, with you to go over some of the details around set theory and Venn diagrams. So before we begin, I just wanted to let you know that this virtual learning could be a challenge for some of y'all, myself included, just sort of learning the new platform and just be flexible. Um, Things are going to be happening and changing, so just be ready to follow new directions and um, you know, be a part of the team. Okay, so on Ingenuity, you've been learning through lessons and videos, but I wanted to just give you my perspective, and I hope that it um, helps to clarify some of the things that you've probably already learned, but maybe just a different voice and a different perspective. So, the main thing about set theory is that there's this notation. And when I say notation, that these brackets, there's an X here, there's another X, there's this symbol in between, there's this symbol right here, looks like an E. Okay, so this is actually a statement in mathematics describing something. And what I'm going to do right now is just break it down into what each of these mean slowly so that we can see how this notation can be utilized to just describe any sort of data. So S is just really, we're saying this set S. Set is like a group of numbers or data, and we're just going to create this set by setting it equal to this what's in the brackets. So it's made up of X, which is just saying anything, any number, any variable, and this symbol that is the vertical line is just saying such that. So we're saying X is the thing, but what are the requirements of X? So that's the X such that. And this E means an element of. So we're saying X is made up of some requirement. And what that requirement is in this example is that X be an element of all the possible letter grades in geometry. So this is a fairly simple set. I'll show you now what it really looks like if you just break it down into all the possibilities. So what set theory says is that, okay, just group my grades into this list right now. And if I have a letter that is not in this, then it's really not part of the set. And if it is in this, it is part of the set. So really that's it. Is it part of the set? Is it not part of the set? And what we're going to do is manipulate things and kind of test things out to see how we compare sets to other sets and some of the more challenging notation. So really, this is just kind of like how to read it. Set S is made up of X such that X is an element of letter grades in geometry. Okay? So the next thing about set theory is a lot of times we need to know what is the pool of all possible numbers that we're going to just look at. So here I'm going to set the universal set, which is just a term, for, okay, let's only look at positive integers. So what this is just saying is we're only going to look at positive integers. So if someone comes up with what about negative numbers? What about fractions? What about pi? You know, these things are not part of the universal set. So we're just not going to look at them right now, only comparing positive integers. Next, I want to define a set that is part of the universal set. That's what this says right here. Make sure that it's part of the universal set and that it's an even integer. So we're saying S is just going to be even integers that are positive. So here's what that would look like. Now what's this mean right here? 3 periods. That just means that this set really can continue on for a long time. Like before we had the A, B, C, D, E, F, or A, B, C, D, F. That is just all there is in it. Here we have a lot more stuff we can't really show, and that's okay. Now I'm going to define a set R, that R is part of this positive integer set, and it's the integers divisible by 4, meaning that they're going to I divide something by 4 and I don't get a remainder. And that's what this set looks like. So it's 4, 8, 12, 16, 20, 24, so on. I'm not going to list everything out. So just think in your head how this list would look. And now what we're going to talk about are subsets. And a subset is essentially when a group of numbers can be pulled out of the set, but it doesn't include everything from that original set. So R, all these numbers, 4, there it goes right here in this set. 8 is in this set. 12 would be in this set as well. So all the numbers in R are also in S. All the numbers in R are also in S. That's what this means. R subset S. R is a subset of S. But not all elements S are in R. So they're not equivalent. It's that R is a smaller group that is all contained in S, but not all of S is in R. So just kind of sit with that for a bit. Subset. Think about it. Subset. When I group a bunch of people, if I say everyone wearing jeans, well, there's people wearing jeans and people not wearing jeans, but the people wearing jeans is a subset of everyone. Okay, next is if I have all positive integers is my universal set. And see how I've written it here? This might be a little easier to look at because it's just kind of defining it with a word. But it's the same idea. I'm just saying give me all positive integers to work with. Next, I'm going to define a set where every element is just the even integers. The elements within this set are just the even integers, like we worked with before. 2, 4, 6, 8, 10, 12, so on and so forth. It will keep going. Now, I'm creating a new notation with this little c that's a superscript, so it's up above like the squared. And this says complement. The C stands for complement. Is every element within the universal element within the universal set, excuse me, every element within the universal set that's not an even integer. So it's kind of like everything that's not in S, but it's in U. I'll define a new set T that is all elements that are odd in the universal set. And what this looks like, of course, is 1, 3, 5, 7, so forth and so on. And we've defined a set T, and we've defined a set S. And here we've kind of defined a new set called complement. But really this is just how you define a complement. A complement is everything that's not included in a set, but is included in the universal set. Now the question is T the complement of S? Is T the complement of S, meaning that if I had all positive integers, it would look like 1, 2, 3, 4, 5, 6, 7. If I pulled out only the evens, would I be left with this set, 1, 3, 5, 7? And the answer is yes, that is what the complement is. Everything that is left over, here we go, everything that's left over when I pull my set out of my universal set. So everything, all numbers, is what we were starting with. I want to take all my evens out, and what I'm left with is the complementary set, and that is my odd number, T. So that's complement. Things that are not ever going to be in the same place. Okay, the last thing is Venn diagrams. And so Venn diagrams are just a simple way to look at multiple sets at a time. So we compare sets A and B using this visual. So I have A on this side, B on this side. And think about it. A is all within this circle. B is all within this circle. But we're splitting it into what is only A, what is only B, and what is both. So here I've created just a sample set, a universal set of numbers, and out of these I want to say A is the negative integers, B are the even integers, but I can also have something that's even and negative. So we'll look at that. So here are the negative integers that aren't even. And I'm just pulling them right out of the set. 11, negative 11, negative 3, negative 1. The next, B, are my even integers that aren't negative. And the overlap, where they are both even and negative, goes on the inside. So using this same data, with Venn diagrams, there's some new notation and terminology, and that's a union. A union is everything that's within every part of both sets. So the union is really just kind of like this universal set, except that it doesn't include any elements listed on the outside of the Venn diagram. So the union, with just this big U, means all elements that are in only A, only B, and both A and B. So the union includes everything inside all circles. Okay, lastly is intersection. And luckily, if you have a Venn diagram, the word intersection really kind of is a visual. That means only elements in both A and B. So here, the visuals, if you look at it, where are these two circles intersecting? That is my intersection of the sets A and B. So it's literally just where I have both negative and even. So it's an and. What things are both A and B? While the union was an or, A or B. So intersection is A and B, union A or B. And just last thing, this is the symbol for intersection. Okay, well, just stay posted. We'll be giving you updates on what will be happening for the rest of this week coming up soon. All right, thank you.